For decades, biology operated on a strict one-way rule. A fertilized egg becomes an embryo, which divides into specialized tissues and eventually forms a mature organism. As those cells specialize, they accumulate damage, lose precision, and slowly decline. Biologists often picture this process using an epigenetic landscape. Think of a sphere rolling down a hill. At the peak, an embryonic cell has infinite potential, but as it rolls down into branching valleys, it locks into a highly restricted role, like a skin cell or a neuron. Once it settles at the bottom, there is no practical route back to the top. In 2006, Dr. Shinya Yamanaka disrupted this assumption. He discovered that introducing just 4 specific transcription factors, chemical signals that turn genes on or off, could reprogram a specialized adult cell back into its earliest state. These 4 signals, now called the Yamanaka factors, forced mature adult cells to travel backward up that developmental slope. A specialized adult cell could actually be returned to a highly flexible embryonic-like state. Researchers soon began testing these newly reprogrammed cells using epigenetic clocks. These are tools that track chemical patterns on our DNA to calculate a cell's exact biological age. This graph charts those age signatures. When scientists measured the reprogrammed cells, the markers didn't just dip slightly. The data plummets perfectly to the baseline, showing that the molecular age of the cells had returned to 0. Science had demonstrated that cellular age could be reversed at a molecular level. But this raises a problem. If the mechanism exists to return cells to 0, why hasn't this cured human aging? To answer that, we have to look at what cellular identity actually is. A complex human body relies on strict layers of epigenetic instructions to ensure a liver cell keeps acting like a liver cell through decades of division and repair. The paradox of the Yamanaka reset is that achieving youth requires erasing those instructions. The cell gets molecularly cleaned, but in the process, it completely forgets its functional role. In the laboratory, that flexibility allows for incredible stem cell research. Inside a living organism, it is a catastrophe. A heart cannot beat and a brain cannot think if cells suddenly revert to an unspecialized state. When you fully reprogram cells in a living body, biological organization breaks down. Instead of healthy young tissue, this instability triggers chaotic growths called teratomas, tumors containing mixed, randomly generated tissues like hair, bone, or muscle. Researchers hit a wall. Attaining biological youth appeared to require destroying the specialized organization that keeps an organism alive. In 2016, researcher Alejandro Ocampo proposed a way around this problem by testing a concept called partial reprogramming. This diagram outlines the precise mechanism his team used. Instead of leaving the Yamanaka factors on until the cell reached an embryonic state, they cyclically activated them. They turned the factors on just long enough to clean up damage, switching them off before the cell lost its identity. As the timeline shows multiple cycles, cellular senescence drops. In live mice, this lowered DNA damage and improved aging markers without triggering tumors. 4 years later, a team led by David Sinclair provided evidence that partial reprogramming could lead to actual functional tissue recovery. Sinclair's team used a modified reprogramming combination that excluded a cancer-associated factor. They applied this therapy to the damaged optic nerves of aged mice suffering from vision loss. The damaged optic nerves physically regenerated, the cellular pathways repaired themselves, and the aged mice regained their sight, a level of recovery previously believed to be impossible in mature mammals. Aging is more plastic than our earlier models allowed. Tissues are not simply decaying blindly. Under the right regulatory conditions, they can regain functions they had lost. This forces us to step away from the traditional view of getting older. For a very long time, we treated aging as simple mechanical wear and tear, like a machine with parts wearing out over time. The information theory of aging illustrates an alternative. On the left, physical gears grind down. On the right, aging is digital data becoming scrambled. But notice the refresh process. Youthful instructions never fully degrade. They are merely obscured, awaiting reactivation. We know that getting enough sleep, reducing stress, limiting calories, and exercising are effective ways to improve your health span. But there is a distinction in how these methods function. Traditional health habits slow the accumulation of damage. Reprogramming actively restores an earlier molecular state. Applying this to humans remains very difficult. We face hurdles including managing cancer risks, preventing unintended epigenetic side effects, and figuring out how to safely deliver these factors to trillions of human cells. Human mortality is still a reality. We will still age, and we will still die. But our bodies are not just decaying machines, passively wearing down. At the deepest biological level, our cells retain a latent organization. They still carry the memory of youth.
Thank you for watching. If something in this resonated with you, then you're already closer than you think. If you're ready to go deeper, there's a link below to my book, The Survival Self: How Childhood Adaptation Becomes Adult Identity, and How to Finally Live Beyond It. This isn't theory, it's a framework you can actually use. Tap the link below and step into it.